Hello everyone, and welcome to the third lecture of the second week. This is the first lecture where we're going to start working with data. Thus far, we've been working really just in pure Python, and the goal has been to introduce you to a lot of the fundamentals that are required for writing kind of any program in Python. But now we're going to be turning our attention to more data-centric topics. And the first thing we need to be able to do if we're going to work with real-world data is to be able to read it into Python. So we're going to start with this WQ.io notebook. I/O stands for input output. So we've only been working with data that we make in Python. Always it's been some variable equals something that we've typed out. We have other notebooks where we generate random data, but usually we're going to be wanting to work with some kind of real data that is a measurement of something out in the world. Otherwise, we're just kind of playing number games by ourselves. So to import data into Python, we're going to need to be able to read files. And the way that we can interact with files on our system are using the Python commands open and close. So on your machines, there is a directory called data. And in data is a sample.txt file here. And we can see there's 3 lines in this file. It's a very simple file. And we can read that into Python by opening it and reading it and then closing it. So we read in the data, and when we print the data, we see, hello, congratulations, you've read in data from a file. And that's all well and good, but in addition to creating this data variable, we also made this f variable. What's that about? This f variable is what's called a file handle. It is a Python object that attaches to a file on our system and lets us interact with it. So we interact with the file through this file handle object stored in f, or referenced to with the name f. And we can see when we print out f, we have a closed file, data sample text, mode R, that's here, at this place in memory. So f is an object in memory that refers to a file on disk. So we will create file handles by opening files, and once we are done doing whatever we want to do with them, whatever we want to do with the file, it is a good idea to close that connection to release the file. There's a number of reasons we want to do this. Chief among them is that many times opening a file will place a lock on that file and prevent other programs from interacting with it. So if we open a file and never close it, then the next time we go to open that file with some other program, we might encounter a problem. Also, it helps us avoid things like accidentally overwriting files or doing other nasty stuff because we forgot the file was still open. So, since we'll always want to follow a pattern of opening a file, doing something with it, and then immediately closing it, there is a handy syntax for doing that all together using Python's with keyword. So with opening this file as f, that says we're going to call this open file handle f. We will do something with the file. And then at the end of this body, at the end of the with statement, the file is automatically closed. So we see the exact same thing here that we had up here, although the address in memory has changed. We open the file, printed out its contents using f.read, and then once we were done with that, the file automatically closed. Nowhere did we have close, but we can see we have a closed file handle when we print out f. So we've been reading entire files using read, but we can also read files line by line. So we can use the read line method to read out just a single line, or read lines to read out all the lines into a list. So here we have a list with hello, congratulations, you've read data from a file. When we use f.read, f.read results in a single string. It reads in the entire file into a string. So read lines reads line by line into a list. Read reads the entire thing into a string. These \n's are what are called new line characters, which is why when we print data, we have hello, new line, congratulations, new line, you've read data from a file. So far, we've been opening files and reading them. And accordingly, we've been opening files with the read mode. So we have this little R flag that signals we're opening this file for reading. We can similarly write to files by opening them with the write mode. So we'll open a new file called mydata.txt. We'll open that as f, and then we'll write some lines to it. So currently, there's no file in here called mydata. So we open the file, write some things to disk, then it's closed because we end the with. Then we open it again for reading and print out what we read in. So we see this is a new file. I am practicing writing data to disk. And that file now appears in the directory. Notice we wrote on multiple lines of code, but it didn't write to different lines of the file. To get different lines in the file, we would need new line characters. And you can also notice that even though I ran this cell again, it didn't, I can run this many times and I get back the same thing each time. Every time I open this file for writing, it overwrites the file. It doesn't add on to the file, it completely overwrites it. So another thing I'll often want to do is append to a file. Not overwrite it, but add to it. And for that I use the A flag for append. So I can open up my data.txt in the append mode and add a new line to the file. We should always be very cautious and careful when we are opening up a file for writing, because we could overwrite our data. So whenever you are opening with the W mode, be careful. You are potentially overwriting a file. I often encounter errors when working with files on disk. And one of the most common ones is an I/O error, where maybe I try to open a file to read it, but there is no such file. So if I look in the directory, there's no file called fail.txt. So I can't possibly open it for reading. It doesn't exist. Another way that is one commonly encounters I/O errors is by opening a file with a particular mode and then trying to do some other kind of action. So if I open a file for writing, I can't read it. Notice in the traceback, when I opened for reading, the error was the with statement, because I can't open a file that doesn't exist for reading. I can open a file that doesn't exist for writing, right? That's just creating a new file. So that's perfectly valid. Instead, the traceback points me to f.read. File not open for reading. It's open for writing. So a subtle difference in the error message pointing us to different locations for the errors. Now fail.txt exists because I did successfully open fail.txt for writing. I only hit an error once I tried to read from it. Likewise, if I open a file for reading and try to write, I'll hit an error because it's not open for writing. You might be frustrated by the fact that if I open a file for reading, all I can do is read. If I open for writing, all I can do is write. Why can't I do both? First of all, it is possible to do both. If I, for instance, open this in the W plus mode, now I won't hit an error. So I needed to comment this out because this is expecting an error. So maybe what I'll do instead is copy this below, eliminate this. So this runs without issue. I can run this many times. You see the counter incrementing over here. Now there's nothing in the file, so there's nothing to read, but trying to read the file doesn't give me an error anymore. Actually, I don't need to, let's do it this way. So this runs, but it exposes a funny fact about
file writing. So I have file.write. Now I can read and write. And when I read, nothing happens. It doesn't show me anything. And that's because write doesn't actually push information to the file. It puts it in a buffer that needs to be flushed before... Well, this is curious. Really? It's there. Now I'm perplexed. Okay, I'm not sure why this is not working. But anyway, at least you can see write and read are both executing without issue. However, typically we won't need to write and read to a file. And also, this is in general behavior that we will want to avoid. We don't usually want to be simultaneously reading information from a data structure, whether that be in memory or on disk in a file, and simultaneously be changing it by either mutating the object in memory or writing to disk. So usually we don't want to do this, which is what my second comment was going to be. The whole point of these modes is to protect you. If you are reading from a file, you don't want the information in the file, usually, to change as you are reading it. That can cause issues. So for instance, I think here what's happening is I'm writing to the file, and it could be that the cursor in the file is past this phrase. So when I read, I'm already past it. And one thing we could imagine going wrong when reading and writing is that our cursor gets out of place, and we either write information where we don't intend to, or start reading where we thought we were somewhere else and miss data that's in the file. So reading and writing simultaneously to a file will usually result in confusion for us. So, often we will want to avoid at least this error, no such file or directory. We will want to read files, but maybe we need to read a large number of files, and we don't know all of their names or if they exist. So we'll often need to rely on a module called OS for telling us what's in the file system. And we can use OS to navigate and act on the file system from Python. So for example, I can use listdir to list the contents of the current directory. So this dot refers to the current directory. And in this directory, we have some different notebooks corresponding with, well, exactly what we see here. And we also have some directories like data and mini projects. listdir is the most commonly used function for inspecting the contents of a directory. There is a more complicated one called walk, which recursively steps through or walks through all the subdirectories of the current directory. I'm not going to demonstrate how to use it. It is very useful, but it is somewhat difficult to get used to using. And in most cases, you can work out a solution for whatever you're trying to do using listdir instead. So for instance, we did listdir on the current directory. We saw this data folder, and directory, and if we wanted to know what was in data, we could just ask for what's in the current directory / data. And it shows us all the files that we could possibly open and play around with. So we know how to read and write, and now we know how to inspect our file system. Let's talk about some actual data formats that we might encounter. So one of the most common formats for saving data is what's called a comma-separated values file. So here is such an example, and it's just a little table where the rows are separated on different lines and the columns are separated by commas, hence comma-separated values. So we have index, name, and age, and below we have indexes 0, 1, 2, some names, Dylan, Terrence, and Mia, and some ages, 27, 54, and 31. And this is a very common format for representing tables. Microsoft Excel or Google Drive, Google Sheets, will both happily export tables as CSVs. This is also, we should note, just a text file. This is just text. If I were to open this file up, you can see it's just text, and I could type anything I want in there. So this is actually ends with a .txt extension. There's no actual meaning to extensions in Unix-based operating systems, but as a matter of convenience or habit or convention, I've included this .txt. So if we wanted to parse this into a table, what might we do? Well, we could, for instance, represent each row of this file as a list, where each element of the list are these comma-separated values, right? You can imagine just throwing brackets around this thing and having a list, 0, Dylan, 27. So we would have a list of lists. Each row is a different list. But then in order to do that, this is just a string. You can see it's just a string with new line characters and commas. So we're going to have to parse this string, meaning interpret this string and impose structure on it. So first of all, let's make our data structure to hold the table. So I've made a list table here, which is just an empty list. And then for each line in the file, I'm going to read it in line by line. For each line, I'm going to append that line where I've stripped out extraneous white space and I split it on commas. And I end up with a list of lists where each element of the list is a string corresponding with kind of a column of this table. So, for instance, we might read in a single line of the file, which looks like this. I'm actually going to have here, I'll set line equal to this, which is one of the lines of the file. Dot strip is going to remove this white space character, this new line. Dot strip removes trailing or leading white space. If we had spaces or new line or tab characters either at the end or beginning of this string, strip gets rid of them. And then dot split will take this string and break it up based on whatever character we put here, in this case commas. So it's going to break this string up into 3 pieces, since we have 2 commas, and return a list. We could choose any character here. I could split on the letter L, and then I would get 0, dy, and then an, 27. The piece before the L and the piece after the L. But since we're dealing with comma separated values, we want to split on the commas. So this gives us a nice list of lists to represent the table. I'm going to skip this for now. I will come back to this in the future. So some of you, at this point, we've gone over much of the Python portion of the course. There's still one notebook we haven't gone over yet. But you should be able now to complete the IP mini project. And some of you have already moved on to the mini project in Python DS, PW. And in PW, we have you download some data and read it in. And it's data composed of a combination of lists and dictionaries. Boo. Let's close some of these running notebooks. Okay, there we go. So you can see that the data is stored as a combination of lists and dictionaries. Really a list of dictionaries. And we ask you to calculate some different quantities from this data, some interesting quantities. The files that we store this data in are JSON files. which we'll talk about now. So we give you some code to deal with these gzipped or compressed JSON files. And now you're going to learn why this code appears the way it does. So JSON stands for JavaScript Object Notation. It's a very common data format, principally because it is used extensively with JavaScript, which is a very common language for web applications. So JSON files are text files that are passed around frequently on the internet between different applications online. And a lot of data on the internet exists in JSON. If you pull data from Twitter or Google Maps, you're going to get that data in JSON. And JSON is really just the data structure built out of nested dictionaries and lists. That's really all there is to it. So let's look at an example that we make, and then we'll also consider an example downloaded from the internet. So maybe I am a librarian, and I am responsible for managing the data at the library on what books we have and whether they are checked out, what condition they're in, all that sort of thing. So to describe a book, I might use a dictionary with different fields or keys describing kind of the different data I might want to include about the book, and then values for what it is that actually describe the book. So I might have The Prophet by Khalil Gibran, so title and author. That's a book of poems. I maybe have some tags for searching. If people were trying to find, books of poetry by Lebanese authors, Lebanese poets, tagging this book with Lebanon would help them do that. Additionally, I might have a list of copies of the book that are at the library. So I might have dictionaries for the information pertinent to the individual copies of the book. How many times has it been checked out? Is it currently being borrowed? What year is it from? These might let us know, do we need to replace one of our editions or buy new copies? And of course, is it available or not? And then I have another book, The Little Prince by Antoine Saint-Exupéry, which is similarly described. There's a discrepancy here. I'll have this be book ID so it matches this one. This second book, one of the copies is borrowed. So it additionally has a due date when it is due back. And when I developed this content, it was, it wasn't that long ago. I think I meant this to be 2018. But anyway, I think I developed this content back in December of 2017. So I was thinking maybe if someone borrowed a book for a couple months, we'd expect it back in early 2018. And then we can construct a library, which is just like a list of our books. And this is starting to look like what we encountered in the PW Mini project, a list of dictionaries. So we have our library with some books in it. Those books, have different properties, and some of the properties don't exist for both books. So the Prophet, neither of the copies are currently checked out, but one of the copies of The Little Prince is checked out, so it has a due date property, or field, or key value pair, which the Prophet does not. Now, one of the nice things about JSON and kind of dictionaries or lists in general is they are structured, but they are not like tables. So we don't have to replicate very much data. So for example, we can represent our library this way, but we could also try and represent it as a table. So let's look at what this would look like as a table. It would have 4 entries, 1 for each copy of each book. And because I have one, I need to be able to describe each copy, I need a row for each copy. But that also means I need to repeat a lot of information. Both copies of the Prophet and both copies of the Little Prince will have quite a lot of the same data, the same title, author, ID, genre, tag. Where they will differ is only the information about individual copies, edition year, checkouts, and whether they're borrowed. So only these 3 columns can potentially have, or would be expected to have, unique data. These other columns are almost guaranteed to have duplications. And that's inefficient. I'm wasting resources storing all these repetitions, whereas in this structure, I only store those once. And then I simply have only the information that differs by copy, broken out by copy. Additionally, we have a bunch of null values. This due date field only exists when borrowed exists. And so all these places where borrowed is false, due date is null. So that's also not very efficient. The 2 big pitfalls, or things you have to watch out for when representing data in a table, is duplication and sparsity, meaning having a lot of null values or a lot of missing data. Because both of these are very wasteful. We spend resources storing repetitions or storing nothing at all. Since JSON is frequently used on the internet, we want to be as compact and efficient as possible, so we don't have this duplication. But it does mean that the structure is a bit more hierarchical and a bit more complex. It's a bit harder to understand at a glance than a table. The main advantage of the table is I can look at this and very easily get an idea of what's going on. When I look at this, it's very hard for me to tell what's going on. So if we want to write what we have here to disk, right now this is just in memory. This is just an object in memory. There's nothing about this on disk. So if I were to restart my kernel, then I would lose this. So if I want to write this to disk, I'll have to use the JSON module. There's a number of JSON modules. there's JSON, there's UJSON. Quite frankly, I don't remember what this U stands for. And there's simple JSON, which I believe is a somewhat limited version of JSON, but I honestly do not remember really what the difference between these three is. I believe UJSON is slightly faster than JSON, but all three are very similar. In the PW Mini project, we have to use simple JSON for reasons that I'm haven't entirely sorted out. But if you use plain JSON or UJSON, you will crash your kernel when you try to parse this simple scripts file, or scripts sample file. If you use simple JSON, there's no problems. Why? I'm not really sure. In this case, we'll just use the plain JSON library, which is part of the Python standard library. Simple JSON and UJSON are not, only JSON. But we do have UJSON and simple JSON installed on your machines. So we'll open up a file for writing called library.json, and we're going to use the JSON module to dump this data structure, library, to disk. And now this file exists on disk. And it's just a text file. If I open up the file, it's just text. I can put anything I want here. There's nothing special about the format of this file. It's just text. But library is not text. It's not a string, it's a list, and it contains dictionaries and more lists. So what the job of the JSON module is to parse between data structures like lists and dictionaries and excuse me, string representations of those things according to the JSON format, which is these brackets and curly brackets. So that's the point of the JSON module. And we can read it back in by opening up that text file and using json.load, which will parse the text and construct the data structure. So here we have the data structure. This is a list containing dictionaries. If we don't use the JSON module, it's just a big string. The JSON module takes this string and parses it into this data structure. I'm going to skip this part and talk about compression. And compression is maybe the last thing I'll discuss in this lecture. We will come back to this notebook in the future, but not until we've learned some other things. Okay, so disk space is limited, like any resource. Bandwidth is limited, like any resource. How fast we can send data, or the rate at which we can send data over the internet, is limited. The amount of data we can store on a hard disk is limited. And in order to alleviate or reduce the amount of resources we use when sending data over a network or when writing to disk, we will often compress our files. And often there are patterns in data that will help us compress them. We can use the patterns to represent the information in a more efficient way. So for example, consider this list of numbers: 10, 10, 10, 2, 3, 3, 3, 3, 3, 50, 50, 1, 1, 50, 10, 10, 10, 10. So that's 18 integers. But we could represent the same information with just 14 numbers. 3 tens, 1 2, 5 threes, 2 50s, 2 1s, 1 50, 4 tens. Now that's not much compression, but it's some. We got away with 14 numbers instead of 18. When applied to much larger files with more significant patterns, we could be much more efficient in compressing the data using a pretty similar scheme, a pretty similar approach. So here, the first number is the number of repetitions, the second number is the actual value. There is a similar algorithm called the deflate algorithm, which looks for patterns in text and uses references to places in the text and how many characters appear in the pattern to represent repeated patterns. If you're curious about the deflate algorithm, there's a link in the notebook to a very nice description of how it works. And the deflate algorithm is used by one of the most common compression formats, which is gzip. You've probably encountered zip files. Gzip is similar, but it's much more common in Linux or the Unix-based computing world, which is where much of software development is done and where much of data science is done. So gzip is a bit more common than zip in data science, or at least common enough that it will be the focus of our discussion. So let's see gzip in action and how we use it to compress files. We're going to download from archive.org the Epic of Gilgamesh. And let's see here. Where did we save that? .data, eog, dejavu.txt. Yeah, so here it is. Here's the Epic of Gilgamesh. It's not so... Oh, here we go. So here's the text. There's a bunch of HTML related to formatting a web page, and then here we have the text in English. So we could open that file and read it into a string. Okay, not quite what I was hoping for. So, let's see. There we go. So here's some 100 characters from the story. if we wanted to compress this string and write it to file, we would open a file with the gzip module. We would use the gzip module to open the file. We'll open it in write mode, but we'll also include this B to indicate binary. We're going to be writing a compressed file. It's not plain text. We use W for plain text. If we are writing anything that's not plain text, then we are probably just writing bits, just a stream of bits. And bits are binary, 0 or 1. So we're going to open this to write binary. And then we'll write to this file that's been opened with gzip. And if we look at the files Epic of Gilgamesh.txt and Epic of Gilgamesh.txt.gz, we see the compressed version is about 1/3 of the size of the original. So compression depends upon patterns in the data. So we were able to compress the Epic of Gilgamesh to 1/3 of its size because language has a lot of patterns. Phrases get repeated, words get repeated. If we were to take all the letters and scramble them, mix them up, randomize them, we see a smaller compression factor. So when we scramble the text and write a compressed file, we only compress it to about 2/3 the size of the original. So compression does not perform well on data with a lot of randomness. Compression is most useful when data is repeated. Compression also doesn't work very well on data that's very small, because small data can't contain many patterns. There's not enough data for patterns really to exist. So, in fact, for this short text file, which has 5 letters, it occupies 5 bytes on disk. But the compressed file occupies 40 bytes. It's actually larger than the plain text representation. And that's because compression has some overhead to it. Compressed files have headers. And since the text is so short, there's really no patterns to take advantage of in compression. So the small overhead, it's not very large. It's only like 30 bytes. Hardly anything at all. But it's the data itself is so short, so small, that the overhead is actually larger than the data we're trying to compress. So if we inspect the file, we can actually see this header. So the file is kind of gobbledygook. It's nonsense because it's not a plain text file. It's a binary file. But there is a header here, which includes a plain text representation of the name of the file. So that's a brief introduction to data formats, as well as reading and writing files. Like I mentioned, we'll return to this topic in the future as we introduce more tools for working with data, which often have their own methods for reading and writing. Next lecture, I'm also actually going to pick up with serialization. I unfortunately don't have enough time. We have maybe I could, of course, go a few more minutes in the lecture and cover this topic as well. But actually, let's just do it. Yeah, let's just do it. Okay. So one last file format I want to discuss is called Pickle, which is sort of a funny name and probably a file format you have not heard of before. And that's because Pickle files are specific to Python. So often we'll want to save complex Python objects. Not just lists and dictionaries, which we can represent using JSON, but things like machine learning models, which are objects in Python that don't have any simple plain text representation that we could possibly put together. In that case, what we want to do is serialize the object, meaning take the object and turn it into a stream of bytes that we can then read back into memory later. And that process of streaming an object from memory into bytes on disk is called serialization. So the Python module for serializing objects is called Pickle. And Pickle is a magnificent tool for writing Python objects to disk and recovering them later. Say we train a machine learning module for several hours, but we need to shut off our computer and go somewhere. And we don't want to lose the state of this trained model, so we serialize it to disk. And when we open up our computer again later, we can read it back into Python, into memory, and start working with it again. So we're going to pickle this object, which is complicated, although it could be represented as JSON, except for this tuple, which would have to be turned into a list. We can't store this as text. Like I mentioned, there is no simple text representation of this thing, and it's not a string. So if we try to write this to file just straight ahead, Python complains that it was expecting a string or a character buffer. It was expecting us to write text. That's what the JSON module is for stuff like this. It turns it into text. Instead, what we'll do is we will use the Pickle module to, instead of turn it into text, turn it into a serialized stream of bytes. So we'll import Pickle, we'll open the file writing as binary, because it's going to be a stream of bytes, and we'll dump this data structure to the file using pickle.dump. And we can load it back in by opening reading binary and using pickle.load. Fairly straightforward. And what we get back, the reloaded example, is identical to what we started with. Python is able to exactly reconstruct the object in memory from this representation on disk, from this Pickle file. The two are exactly the same. Pickle is a really useful tool, like I mentioned. It's often used for storing machine learning models or data sets, or really almost any Python object. Anything that is, some kind of complex Python object, we will usually write to disk in the Pickle format file. So that's going to conclude our lecture. We will be returning to this notebook in the future. But now, hopefully, you know how to read and write data to disk.